Hello everyone. Let's start with a little curiosity. Have you ever played with a magnifying glass under the bright sun and seen how it can focus light so sharply that it burns paper? Or maybe you've noticed how a concave lens in spectacles makes distant objects look smaller. The secret behind both lies in the way lenses bend light. Now, here's something fascinating. Unlike a mirror, which reflects light only once, a lens bends light twice, once when the ray enters the lens, and again when it exits. That double bending is what gives lenses their power to focus or to spread out rays. Today, we'll focus on two special types of lenses. The equiconvex lens, where both surfaces bulge outward equally. This lens gathers light rays and brings them together at a point. That's why we also call it a converging lens. And then there's the equiconcave lens, where both surfaces bend inward equally. This one does the opposite. It spreads light rays apart, so it's called a diverging lens. One collects, the other scatters, a bit like two friends with totally opposite personalities. But to really understand how and why lenses behave this way, we need to learn a few powerful but simple lens terms. Think of them as the alphabet of lens optics. Without them, all the formulas and diagrams would feel like reading a mystery book in a language you don't understand. Okay, students, a light ray is about to begin its adventure. Imagine a curious traveler leaving the wide-open air and stepping into the heavy glass door of a shopping mall. What happens? It slows down, changes direction, and bends. That's exactly what light does when it enters the first surface of the lens. Here, the medium changes from air, which is rarer, to glass, which is denser. And nature says, if you change the medium, you must bend. This bending is explained by the law of refraction, also called Snell's law, which states n1 times sine of I equals n2 times sine of r. In words, the refractive index of the first medium multiplied by the sine of the angle of incidence equals the refractive index of the second medium multiplied by the sine of the angle of refraction. Simple rule, but very powerful. Now, how much the ray bends doesn't just depend on Snell's law, it also depends on the radius of curvature of the first surface, called R1. You can think of it like the slope of a slide in a playground. A steeper slide makes you zoom down quickly, a gentler one bends your path slowly. And here's a neat fact, in equiconvex lenses, R1 is equal to positive R. But in equiconcave lenses, R1 is equal to negative R. So whether the ray bends inward like a warm hug or outward like a push depends on the shape of that first surface. So, at the first surface, our ray's journey begins with a bend guided by Snell's law and the curvature of the lens. Think of it as the opening scene of a movie. The suspense has just begun. Alright students, let's keep tracking our little light ray. After bending at the first surface, the ray continues its journey inside the glass and soon reaches the second surface of the lens. Now, something interesting happens. The ray is moving from glass, which is denser, into air, which is rarer. Think of it like leaving a packed school bus and stepping into an open playground. You suddenly feel freer, and so does the light. But remember, nature always enforces its laws. Here, the ray must once again obey Snell's law, which says n1 times sine of I equals n2 times sine of r. That means the refractive index of the first medium multiplied by the sine of the angle of incidence equals the refractive index of the second medium multiplied by the sine of the angle of refraction. And here's the secret director of the show, the curvature of the second surface, called R2. This curvature decides where the emergent ray finally goes. Does it spread out, come together, or continue straight? All of it depends on that curvature. That's why lens makers are so precise. Even a tiny change in the second surface is like wearing glasses with the wrong prescription. Suddenly, the world looks wobbly, like a carnival mirror. So, the summary is, at the second surface, the ray bends again following Snell's law, and the curvature R2 decides the grand final of the emergent ray's path. Alright students, our light ray has completed its bending act at both surfaces of the lens. Now let's put the whole story together. When we consider both surfaces, we get a relationship between the focal length f, the refractive index n, and the two radii of curvature, R1 and R2. This relationship is given by the famous lens maker's equation 1 by f equals n minus 1 multiplied by 1 by R1 minus 1 by R2. This simple-looking formula is like a recipe for lens design. If you know the refractive index of the glass and the curvatures of both surfaces, you can calculate the focal length. Now let's test it in two special cases. For an equiconvex lens, R1 is positive R and R2 is negative R. Substituting these values, we get 1 by f equals to times n minus 1 by R. That means convex lenses are converging. They bring light rays together like friends crowding around a birthday cake. For an equiconcave lens, R1 is negative R and R2 is positive R. This gives us 1 by f equals negative 2 times n minus 1 by R. The negative sign here is the big hint. Concave lenses are diverging, pushing rays apart, just like students running in all directions when the teacher says, "Pop quiz." So, the bottom line is, convex lenses focus light, concave lenses spread it out, and the lens maker's equation shows us exactly why. Alright students, time to meet the star of optical devices, the equiconvex lens. When light rays that are parallel to the principal axis hit this lens, they don't just wander around. Instead, they all converge at one point called the principal focus, or simply F. It's like friends planning to meet at one cafe after school. No matter where they start from, they all end up at the same spot. Now, what decides exactly where this focus will be? The focal length. And the focal length depends on two things: the refractive index of the material and the radius of curvature of the surfaces. In other words, the material of the lens and how curved its surfaces are. Here's the equation that lens makers love: 1 by f equals to times n minus 1 by R. This tells us that the sharper the curvature or the higher the refractive index, the shorter the focal length. And here's a real-life use: cameras and projectors rely on equiconvex lenses for sharp focusing. So, next time you watch a movie on a projector, hang the humble convex lens for that crisp image. Without it, your film night would look like a blurry watercolor painting. And don't forget, convex lenses are converging lenses, while concave lenses are diverging lenses. The convex one brings rays together like best friends, while the concave one pushes them apart like siblings fighting over the TV remote. Okay students, now let's flip the story and talk about the opposite of a convex lens, the equiconcave lens. When parallel rays of light enter this lens, they don't meet at a point like before. Instead, they appear to diverge from a principal focus F on the same side of the lens. It's like students trying to gather for a group photo, but everyone keeps walking in different directions. No group picture today. Here's the key difference: for a concave lens, the focal length is negative, which directly shows its diverging nature. The negative sign is like a warning label. This lens doesn't bring things together, it pushes them apart. The equation for an equiconcave lens is 1 by f equals negative 2 times n minus 1 by R. That minus sign is very important. It's the mathematical way of saying this lens diverges. Now let's connect this to real life. If you've ever seen spectacles for correcting short-sightedness, they use concave lenses. These lenses spread out incoming rays before they reach the eye, helping the person see distant objects more clearly. Without them, the world beyond a few meters might look like a watercolor painting. So, while convex lenses act like a magnifying glass focusing sunlight to a sharp point, concave lenses are the exact opposite. They spread light out. In short, convex lenses are gatherers, concave lenses are scatterers. Both are equally important in the world of optics. Alright students, time to tie the whole story together. Let's quickly summarize what we've learned about refraction in equi-lenses. First, remember that refraction doesn't happen just once in a lens, it happens at two spherical surfaces. The ray bends when it enters and bends again when it leaves. Like a student passing through two doors, one to enter the classroom and one to exit, each door changes the direction slightly. Next, in an equiconvex lens, the rays converge and meet at a point. That gives us a positive focal length. Think of it as a magnifying glass focusing sunlight to burn a piece of paper, convergence in action. On the other hand, in an equiconcave lens, rays diverge. They spread out as if they're running away from a focus on the same side. This gives a negative focal length. And that's why concave lenses are perfect for spectacles correcting short-sightedness. Without them, reading the board in class would be a nightmare. Now, we can't forget the lens maker's formula, which connects focal length f, refractive index n, and the radii of curvature R1 and R2. It's the blueprint for making lenses with exactly the power we need. Finally, the applications are everywhere: cameras, microscopes, telescopes, projectors, and even the glasses on your nose. In short, lenses are the unsung heroes of science and daily life. So here's the takeaway: convex lenses bring things together, concave lenses push them apart, and the math behind it is neat enough to fit in one powerful formula. That's the beauty of physics: simple rules, huge impact.